Hi there, I'm Vinicius Gonçalves, and now I will present to you our project named Influence of Pore Geometry Assumptions of the Plug Scale Permeability. At first, we have a little introduction about the subjects and the main concepts of the project, and then we'll talk about the methodology created and adopted in this project. After we present the results and a little discussion about them, and finally present the conclusions. The matrix acidizing process is commonly used in oil industry to increase the productivity of the wells. Is a stimulation technique based on acid injection into the reservoir formation. The acid is responsible to remove the damage in the near wellbore region. And also in carbonated reservoirs, there is a dissolution of the matrix by the reaction acid-rock. This reaction creates channels increasing the permeability. Flowing porous media and heterogeneous reaction between the acid and the rock are the two main aspects of the matrix acidizing process. In this context, the dissolution point is one of the most control variables, the most important control variables in this process. It's strong dependence of the injection rate. At low injection rate, you have the phase dissolution when the acid don't penetrate enough in the formation. At high injection rates, you have the uniform dissolution, or when the acid reacts with the entire domain. The most suitable dissolution pore is named as wormhole. If you represent the relationship between the flow rate and the volume of acid used to perform acidizing testing experiments, you have the optimum injection rate when you have the dissolution pattern like wormholes. In the optimum injection rate, you have the minimum volume of acid used to perform the stimulation process. And because of this, wormhole is the most suitable dissolution pattern for the process. And modeling wormhole is one of the most important tasks in the research. And in your project, we needed first decide how to model the flow in the porous media. The first model is a network model. In this way, we can imagine the porous medium like as a network of tubes interconnected to each other. This model allows to describe the dissolution patterns and also predict the optimal rate flow in good agreement with experiments. But network model has a big limitation. There is a high computational cost associated and use this model to do simulations. And because of this, we take a view on a continuum model. The continuum models are two-scale models that describe the dissolution at that scale, and the dark scale needs the information of the pore scale. For example, the topology of the pore choice. They are computationally more efficient than network models, and we have good results in agreement with the experiment. And thus, we have some main goals and assumptions for this study. We use a continuum model to describe the flow in pore medium. We don't consider at first a reaction between the pores and the flow. That means the acid flows within the porous medium with no reaction. We adopt Newton generalized rheological models like Pore law, for example. And the main objective is to test the influence of the pore scale model and plug scale permeability. And the continual model adopted is the theory of the mixtures. In that theory, it treats multiphasical systems, and we have for each system as a component of a mixture. It's assumed that each component of the mixture occupies the same spatial domain. Each component of the mixture has or single equations of conservation, of mass conservation, of momentum conservation. Here we have the mass conservation. And since we don't have a reaction, the right side term of this equation vanishes. Here we have the momentum conservation equations, where Bi is a body force, like gravity, and Ti is a stress tensor. Mi is interaction term between the two phases in our case, the acid phase and the porous matrix phase. The porosity is defined as a ratio between the volume of pores and the total volume. With the porosity, we can find the density for the phase, for the acid phase, and the stress tensor for the acid phase. Here we can note the importance of the interaction term. The interaction term accounts the acid-rock interaction first, when the acid flows within the porous matrix. It depends strongly of the model, of the Pore scale model, and how to model this. There are two main approaches to model the interaction term. The first is to find analytical expressions. And the second is to treat this model as a numerical approach. The first is an analytical model is to treat the Pore matrix like a set of cylinders and solve the equation of moment. Inside the cylinders, you have this equation for the main velocity. Using the Dor's law equation and combining the two equations, we have an expression that relates the permeability K, the porosity, and the pores radius. If you treat a fluid incompressible using a parallel model and consider the flow inside the cylindrical pore fully developed, we have this expression for the mean velocity, and combined with the expression that relates the permeability and the porosity, we have this expression. The interaction term is equal. The porosity multiplies by the pressure gradient. Combining these two equations, finally we have an expression, an analytical expression for the interaction term. This interaction term is a function of the terms of the fluid, like the polar fluid and the polar index n, or the consistency constant K, and the permeability and the porosity, the velocity. There are parameters of the fluids and the medium also. And now, if you have an equation to express the interaction term, we have the complete equation of conservation, the mass conservation, the momentum conservation for the phase fluid. Now, we present a numerical approach developed to account the interaction term. If you have interaction term as a function of the porosity, the pore volume, and the force, the drag force of between the solid and the fluid phase, we can try to implement or perform a group of simulations using different topologies of pore. In analytical case, we use only the assumption that we have only cylindrical pores. But here, in the numerical approach, we use different topology for the pores, considering topologies of convergent and divergent channels, having different extensional levels. The simulations are used the finite volume method, and safety simulations are used the OpenFOAM software. We use a polar fluid and a range of parameters of fluid and flow. In the geometry, we use 5 types of geometry, and the parameter delta controls the extensional level. When the delta is 0, we have the cylinder, the normal cylinder, as used in the analytical form. When delta is 0.8, we have the more extensional topology. The range of parameters is shown in this table. We have 4 groups of Reynolds number and 5 groups of geometries. Here use also 3 different pores radius and 3 types of fluid. When n, the pore law index, is 1, we have the Newtonian behavior, and we have 0.5, we have a shear thinning behavior, and we have n equal 1.2, we have a shear thickening behavior. The objective of this simulation, the group of simulation, is to obtain the force in the walls of the pore caused by the flow of the fluid. We have a process of dimensionless the value of the force, taking the force obtained and divided by the group. When we see in the results, if we increase the Reynolds number, it's expected to increase the force, and the dimensionless force have the opposite behavior. Here we have the first results using Newtonian fluid for the cylindrical topology of pore and the more extensional topology. You can note that the pore radius has no influence of it in the force. We have found the same results in the 2 cases for the free pores radius used. In this one, we have 3 graphs, and each graph represents a type of fluid. We can see in these graphs that we have a good agreement with the analytical solution. The analytical solution and the cylinders used in the numerical solution are in perfect agreement. We have also observed the great difference between the force when you change the topology of the pore. This behavior is almost the same for the free fluids. Here, you can express the difference between the fluids. You can note that when you have a cylindrical topology, the free fluids have the same behavior, and this behavior come to be different when you put the flow in the extensional pores. When you use the more extensional pore, we have the biggest difference between the free fluids. When these values, we have now plug scale simulations. When you use when used again Newtonian and Pore fluids. We have these three expressions to achieve the permeability. One for cylindrical pores only, the second for the Darcy's law and using only for the Newtonian fluid, and the third using the interaction form in numerical approach to obtain the permeability fields. All the initial and boundary conditions used as in the table, and the porosity field is the same for all simulations. Here we have the results for Newtonian fluid. In the parallel fluid, we have good agreement between the different forms to account the interaction term. Here we have a great difference between the pressure field when you use a different topology of the pore. Conclusions: the methodology for the numerical use of the fluid-pore interaction they proved to be effective and promising. The permeability fields obtained have good agreement whose obtained analytically. The pore scale results showed perfect agreement with the analytical results available for cylindrical pore, and the simulations involving the extension pore geometries show the importance of the discussion about the constitution of the other pores medium in the solid-fluid interaction. The applied pore scales result for different degrees of extension in the plate force simulations are also shown that the pore realization can have a significant impact of the microscopic fields. And finally, the numerical approach proves to be the best way to characterize fluids with more complex rheological behaviors, such as viscoelastic fluids. On alignment, we can thank the team that had developed this work, the supervisors and co-authors of the paper, and thanks to ABCM and organization of this conference. Thank you.